Welcome back, everybody. You may remember our previous video. We introduced the whole idea of stoichiometry, which is the study of chemical reactions and mass changes that go along with that. And we know that stoichiometry is very valuable because it allows us to actually do experiments in the lab and to predict what mass of products we're going to get given a certain starting reactant, or vice versa, how many grams of a certain reactant are required to make a certain product. What I want to do here is to look at two types of calculations that we can do quite easily. The first being finding moles of a product from a known amount of moles of reactant. And from that, we can find the mass of that product from the moles of that product. We might also go in reverse, where we start with products and go back to reactants. So what I've done is I put the same reaction up on the board that we just previously had, and that is the balanced equation for the decomposition of potassium chlorate. And there's 2 moles on the reactant side, and that breaks down into potassium chloride, 2 moles of this, and 3 moles of oxygen. Don't worry that moles are not conserved in chemical reactions. We decided last time that that's okay. It's mass that's always conserved, according to the law of conservation of mass. So we've got on our equation line the coefficients that we have underneath each of these species really is the same as what you see in the balanced equation. And that's really all the balanced equation is. It's a ratio of moles. That's all it is. However, let's suppose I give you 5 moles of potassium chlorate. And without doing too much hard math, we should be able to predict how many moles of products we should get. Well, easily done. If we have 5 moles of this reactant here, then according to the balanced equation, you see that 2 moles of potassium chlorate also produces 2 moles of potassium chloride. So if we have 5 moles of potassium chlorate, it makes sense that we should get the same number of moles of KCl. Why is that? Because they're 1 to 1 in the balanced equation. This one here, in terms of oxygen, is a little harder to do, although I think mental math can allow you to do it. We know that 5 moles of KClO3 makes the same number of moles of potassium chloride. In terms of oxygen, you can see that 3 is greater than 2. So our answer here has got to be greater than 5. It just makes sense mathematically, doesn't it? Well, 3 over 2 times 5, which is 1.5 times 5, ends up being 7.5 moles. You could quickly do the math to figure this out, because 3 over 2 times 5 ends up being our answer, 7.5 moles. Now, this isn't much use to a chemist because we don't have balances in our storage room that weighs moles. We have to weigh grams. So remember from before, we went from grams to moles and moles to grams. Well, now we're going back from moles to grams. So simply enough, the mass of the oxygen, if we were to ask this question, that you would produce in this case is equal to the moles times the molar mass. And we just figured out that there's 7.5 moles of oxygen here. And of course the molar mass of O2, which is only here, the O2, not the 3. This belongs to the balanced equation. This is the mass of 1 mole is 2 times 16. And if you do the math with your calculator, obviously you should have always have your calculator handy. We get 240 grams of O2. So very simply, we can figure out the mass of a product if we know the number of moles that we start with. Now, we can go the other way. If we set up another equation another experiment, and instead of dealing with 5 moles of KClO3, we can deal with 6 moles of O2. So let's start on the product side. And let's suppose the question is, how many moles of KClO3 would be required to make 6 moles of oxygen? Well, this ratio is pretty easy because we know that 6 is twice as big as 3, so our answer would be 4, wouldn't it? So in this case, 4 moles of KClO3 would be required to make 6 moles of O2. We can also go back to grams here, just like we did here. Why is that? Because we know that grams is equal to moles times molar mass, once again. And the molar mass of KClO3 is 122.6. So we have 4 moles times 122.6 grams per mole. And you can check that on your own, but it's right. And that ends up being about 490.4 grams of KClO3. So, there you have it. Fairly quickly, we are able to set up our equation. Our equation line always deals with the mole ratios that we see from the balanced equation. Yes, the equation has to be balanced. The experiment line, in this case, this is really what the question's asking. And this is kind of a unique method that I use to solve problems. The textbook uses a different method. However, I've had good luck with this method, setting things up nice and organized and working underneath. And we can figure out moles from moles, grams from moles, or even working backwards to start with products and ending up with reactants. Hopefully that helped. That's a little introduction to basic stoichiometry, mole to mole calculations, and mole to mass calculations. Our next step involves a little more work. That involves taking grams of reactants and figuring out products in grams, or vice versa. And we'll get to that step. That's section 7.3 in your textbook. And that'll be our next video. Hopefully this helped.